Hello, and welcome to the first in a series of video tutorials designed to show off the functionality of the 555 timer integrated circuit. I'm Dylan Z, and in this tutorial we will dig a bit into the 555, explaining what its main uses are, and then get right into building an adjustable speed DC motor circuit. This circuit will take advantage of the 555's Astable Mode, allowing it to output an oscillating signal which will then drive a DC motor. We'll be using a technique called pulse width modulation in our circuit in order to speed up and slow down the motor as we wish. If you have not already, I recommend you watch my video tutorial on Astable multivibrator circuits, where I demonstrate the function of the Astable circuit without the 555 timer. It's linked here. As with any hobby electronics project, safety is number one. Though the voltages and currents we'll be using pose no real danger, I urge you to check out the two websites shown on your screen for safety tips when working with electronics. The information there is very useful. We'll need a few electronics components and tools to build this circuit. As always, you can find these items at various online sources, including eBay, Amazon, digikey.com, and mouser.com, to name a few. Here are the things you'll need. One 555 timer integrated circuit, one tip 31 NPN transistor, three 1N4148 or equivalent diodes, three 100 nanofarad ceramic capacitors, one 100k ohm linear potentiometer or variable resistor, three wires with attached alligator clips. The alligator clips are not absolutely necessary, but they do make connecting the potentiometer to the breadboard much easier. One 12-volt DC motor. You can see I have mine in a clamp to keep it steady as it's running. I would recommend using one of these or something else to hold the motor in place. One 10k ohm resistor, a 9-volt battery with snap clip, lots of jumper wire. You can make your own or buy them pre-stripped, and a breadboard. You'll also need a few tools to build this circuit. A pair of needle nose pliers, wire cutters, and optionally a multimeter. This comes in very handy for troubleshooting and testing circuits. I want to get moving on building the circuit, but let's have a closer look first at the 555 timer. This IC is perhaps the most famous, certainly the most widely used, with over 1 billion produced each year. It's used in everything from egg timers to video games to space travel. If you open up an electronic device, it's likely you'll find one or two of these things inside. The function of the 555's 8 pins and its 3 modes, astable, monostable, and bistable, deserves its own video, which is upcoming. As soon as I've posted it, I'll link it here. In the meantime, we'll look at just the functions that are applicable to this circuit. Here is a typical 555 Astable circuit schematic. There are other configurations for putting the 555 in Astable mode, but this is the style we'll be using for the DC motor circuit. Note that when shown in a schematic, the 555 timer is often represented with its pins out of order. This is simply to make the schematic easier to read. Just be careful when building a circuit on the breadboard or a PCB from a schematic to make sure you're wiring up the correct pins. Here again is what the actual 555 timer looks like up close. In Astable mode, the trigger and threshold pins are typically wired together. This allows the 555 to trigger itself and provides an endless signal to be generated. As usual with the 555, the threshold pin is wired to a timing capacitor and a timing resistor. The values of these two components can be altered to adjust the square wave output from the 555. Note also in this schematic that the output pin is wired to the timing resistor and trigger and threshold pins. You might expect that the discharge pin should be used this way instead, but there's a good reason for this. The discharge and output pins go high and low in this circuit at the same time, so either can be used as the output pin. However, the output pin can both source and sink current, so it's preferable to use it in this case instead of the discharge pin, which can only sink current. This will become more apparent as we look at the DC motor circuit and run through its design. As I mentioned before, we will be using a technique called pulse width modulation to adjust the speed of the DC motor. In this graphic, you see two separate square waves, each with the same frequency, or combined time, t, of the high pulse and off time. T is also known as the signal's wavelength. You can modify the length of the high pulse with the potentiometer while keeping the same value t, or combined high and off time. With a short high pulse time, the effective average voltage to the motor is lower, slowing it down. Conversely, with a long high pulse time, the average voltage is higher, speeding the motor up. You might ask why you can't just actually modify the voltage to the motor with a variable resistor to speed it up and slow it down. Well, in fact, you can. However, lots of excess heat is generated at the resistor, effectively wasting energy to the motor. Also, the amplitude of the signal changes with this method, which means at slower speeds the motor will actually be less powerful. Using pulse width modulation, as we will do, the amplitude of the signal is always high, allowing the motor to run at full strength even when it's slowed way down. The motor can run much slower without stalling using PWM. For more information on pulse width modulation and the 555, especially if you want to get into the mathematics used to determine the values of the timing resistors and capacitors, check these two Learn About Electronics modules shown on your screen. There is a wealth of detail there on this subject. Okay, let's build this DC motor circuit. Here is the schematic for our circuit. You may find it useful to pause the video here and print this schematic for your reference as we go through the process of building it. First, find a nice place in the center of the breadboard to place the 555 timer. As with any integrated circuit, there is a U-shaped notch on the IC that indicates its pin orientation. Starting to the left of the notch, the pins are numbered in order in a counterclockwise direction. Place the 555 timer with the notch pointing left, so that pin number 1 is the leftmost pin on the bottom of the IC. Also, be sure to place the IC so that it straddles a center line or ravine on the breadboard. This ensures that each pin has its own set of connected holes. I've highlighted the center line in this case in blue. And as with all my tutorials, I've highlighted in red the holes where the component should be placed. This is helpful if the photo doesn't clearly show the proper holes. With components where polarity is a concern, and the photo doesn't clearly indicate the polarity, I will highlight where the positive lead should go in red and the negative in blue. Now wire pin number 1 to ground as shown, and pin number 8 to the 9-volt rail. One thing to note as we're building this or any circuit, the power source should not be applied to the breadboard while we're constructing the circuit. This could lead to damaging components. Next, wire pin number 4 to pin number 8 as shown. I realized after building this circuit that I had placed the top end of this wire in the same hole as pin number 8. Typically you don't want to do this, but it's not really a concern here. However, if you like, since there is enough room on the breadboard, you can place that end of the wire in the hole above where I've placed mine. Now connect one of the 100 nanofarad caps from pin 8 to ground as shown. Next, wire the 10K ohm resistor from pin 7 to pin 8, as you see on the screen. Now wire the second 100 nanofarad capacitor from pin 5 to ground. Pin 5, the control pin, is not used in this circuit, and it's good practice to wire it this way so it cannot interfere with any other pins. Now we'll wire pin 2 to pin 6. Again, I've placed the top end of the wire in the same hole as pin 6, and again, you can use the hole above pin 6 if you like. Moving along, we want to place two of the 1N4148 diodes as you see on screen. Make sure to observe the correct polarity with these. One of the diodes is wired so that its negative lead is connected to pin 2, and the other so that its positive lead is connected to pin 2. The other ends of the diodes are connected to different holes below the 555 timer. Now we'll connect the 100K ohm potentiometer, or variable resistor, starting with the center lead. Connect its center lead to pin 3 as shown. You can see now why the alligator clips are so convenient. Next, connect its left lead to the positive lead of the first diode as you see on screen. Finally, connect its right lead to the negative lead of the second diode. Now let's connect the final 100 nanofarad capacitor from pin 6 to ground as shown. And now connect a wire from pin 7, the discharge pin, and in this case the pin that provides our output, to a hole to the right of the 555 timer. Now connect another wire as you see on screen. It's important to place these wires exactly as shown, as they're being placed in preparation for our transistor. Now connect the third and final transistor wire as shown to ground. Next comes the TIP31 transistor. Place it as shown with the bulky part of the component facing toward you. In this orientation, the pins, starting from the left, are base, collector, and emitter. Pin 7 on the 555 provides the base signal, the collector will be connected to our motor, and the emitter pin is grounded. Now, in preparation for our motor placement, connect a wire as shown, one end connected to the 9-volt rail. Next, we'll wire in the DC motor as shown. Remember, you'll want to stabilize the motor in some way. In my case, I've used a clamp sitting on some books. Now we will place the final 1N4148 diode as you see on screen. This diode is being used to provide a safe path for the inductive kickback of the motor. Because the motor cannot instantaneously turn off, there will be excess current when the transistor switches off, which is almost instantaneous. The diode allows that excess current to flow back through the motor safely, as opposed to its flowing into the transistor. Over time, that excess current could easily fry the transistor. Great! The circuit is now ready for power. Go ahead and connect your 9-volt battery to the breadboard and test out the adjustable speed DC motor circuit. If you wired everything properly, your results should match what you're seeing on screen. You twist the potentiometer one way, the motor speeds up. Twist the other way, and it slows down. Notice that I'm able to slow the motor down even to the point where you can actually see the mark I've made on the Dremel buffer I've attached to it. The motor is running at full power, even at this slow speed. That's pulse width modulation. Let's take a look at the current the motor pulls while this circuit is running. Note on screen, I have my multimeter connected in series with the motor to show its current in amps. The motor requires about 120 milliamps to get started and will pull around 230 milliamps at full speed. Something to keep in mind when powering this circuit with a 9-volt battery. Your typical 9-volt battery has a rating of about 0.5 amp hours and will probably only last a couple of hours with the motor running at full speed. For projects requiring constant running of a motor, you'll need to use a beefier power source. This is a subject I plan to explore in future tutorials. Now let's step through the circuit and examine what happens when power is applied. First, we'll assume the timing capacitor, C3, is discharged and the trigger pin is low. Because of the internal relationship between the trigger pin and its output pin, this means the output pin starts out high. When the output pin is high, the timing capacitor, C3, begins to charge through the right side of R2, the potentiometer, and D3, the right diode. Remember, electrons pass through a diode from its positive lead to its negative lead, but not the other way around. Also, because of the internal relationship between the 555's output and discharge pins, which are always high and low at the same time, the discharge pin is high, causing the transistor Q1 to be turned on, allowing current to flow through the motor. When the voltage on C3 charges to 2/3 of 9 volts, our power input, the threshold pin activates. Again, this is an internal function of the 555 timer. When the threshold pin activates, the 555 timer brings the output and discharge pins low and the trigger pin high. The immediate effect of this is that the discharge pin, because it's low, sinks the current from R1, thus turning off the transistor. Current can no longer flow through the motor. When the output pin goes low, it begins discharging C3 through the left side of the potentiometer via D2. As C3 discharges below 1/3 of 9 volts, the trigger pin goes low, again a function of the 555, which causes the output and discharge pins to go high again. Q1 turns on, and current again flows through the motor, and the cycle repeats itself over and over. The timing portion of the circuit, R2, D2, D3, and C3, determines the wavelength and high pulse time. The wavelength remains constant because the sum of the charge and discharge resistance at the potentiometer is always the same. The high pulse time versus off time changes with the values of the resistance in the potentiometer. The upshot of this is that when you turn the knob, the resistance on either side of the potentiometer changes, adjusting the high pulse time and off time, and thus the speed of the motor. Congratulations! You've constructed a working adjustable speed DC motor circuit using the 555 timer in Astable mode. I urge you to tinker around with the values of the timing resistor and capacitor. You can also use something other than a motor to power in this circuit, say a strip of LED lights or multiple strips. Use your imagination and come up with some interesting modifications to this circuit, and think about practical uses for a hobby electronics project. I hope you've enjoyed this DC motor circuit video tutorial. If you haven't already, subscribe to my channel, that's the Hobby Electronics Mega Channel, and check out my other video tutorials. I'll be posting a do-it-yourself desk lamp conversion project very soon, where I use a very similar 555 Astable circuit to convert an old desk lamp into a new, powerful LED dimmer lamp. I plan to add some exciting features, so check back often for this and many more upcoming video tutorials. I'm Dylan Z, and I wish you the best in all your hobby electronics adventures. So long for now.